Okay, welcome to class, students. Let's begin. For those of you that picked up your exam printout last time, you are squared away. If you did not have a chance to pick up your exam printout, we'll probably have a few minutes after class. Darian, do you still have the printouts? Oh, we got it. Oh, okay, we got them up front here, and Darian, or actually Caroline, will give them out to you at the end of class. For those of you that had a couple blanks, PID problems, those are all squared away now. In addition, Shai is up here in the front. And she says that you're going to have an online SI session tonight, 6 o'clock. Will be recorded. And you'll post a link for the recording in discussions, correct? Okay, good. All right, so if you don't make it, you can still benefit from it, even if you're not actually participating in real time. About the exam. Here's the distribution of performance. I don't normally give a letter grade on a single exam. I usually just give letter grades at the end of the semester. But if I did, this is how the A's, B's, C's, D's, and F's would have shaken out for this particular exam. The average was about where I wanted. I want to get an exam average about 70%. This one was pretty close to that, 35 out of, just a little bit below that, 34.98 out of 50. So that's pretty much 70%. And there's a couple things about this that I'd like to point out to you. First of all, there's the same number of F's on, and this is for students that actually took the exam. All right, so all the bloopers are in here that we didn't have Tuesday. And there's a few people in here that didn't do any clicking, but they did the Scantron, so they have a score. Everybody that took a Scantron and got it graded, they're in. The same number of A's as F's. Now, when somebody grades on the curve, that's one of the things that you look for, symmetry left and right, with the symmetry line being the C's. But if you look at this distribution, you'll see that it's skewed off to the right. That is what we want. And that is one of the reasons that I never grade on the curve, ever. Because my objective is to empty out this section here and get as few people flunking as possible, and then load it up over here. All right? I want to load that one. And all these other the C's, I want the B's, I want to load this one up. And it's already loaded up a little bit more than the D's, actually quite a bit more. The ratio here is 5 to 2. All right, there's 5 times the ratio here, 60 divided by 24, reduces to 5 over 2. So we're doing good, but we still got some people down here in the D's and F's. Want to hopefully push them forward and start loading up the upper range of that. Questions before we go to the circular motion for the day? Okay, let's keep going. Last time we were talking about this situation, I gave you kind of an idealized view of an object on a circular path moving at constant speed, although not constant velocity because the direction was changing. Here are 2 snapshots that include the position vector here, the black radius at two different times, 30 degrees apart, time t1 and time t2, the velocity vector is straight up at time t1, but it's dipped a little bit to the left at instant of time t2. And then I made copies of the two radii and formed a blow-up of the triangle that they formed together, with the tail at the center of this circle and the outer part being out here to the right. And I crossed I formed the base of this isosceles triangle, knowing that this approximate distance of travel is very close to v delta t. V delta t is the exact amount of distance, and that dashed line is close to that distance. It's not exactly the same, because the dashed line is a straight line, whereas v delta t is going along a circular arc for 30 degrees. So it's a little bit longer. Similarly, I took the two velocity vectors and I copied them over here and tail to tail, and I made a velocity triangle. And those two triangles are proportional triangles. They have identical angles. The sides are proportional, and that proportion is going to get the job done for us. So this is basically very close to where we stopped. In the order of position triangle on top, speed triangle on the bottom, here's the proportion that we're going to use. Now, this is the isosceles side of the position triangle, and here's the isosceles side of the velocity triangle. All right? In other words, the long side. All right? And there's the key proportion. Make sure you make a note of that. So here's the isosceles sides. And then this one over here, v delta t, that's this base for the position triangle. The base, the third side of the isosceles triangle. And then delta v is the isosceles base for the speed triangle. And the ordering is the part from the position triangle on top and the part from the speed triangle on the bottom. Now, we could have done it flip-flop of that if we had wanted to. There's no preference there, but this one is comprehensible and it works out fairly nicely. So this is my main proportion here. R over V equals V delta T on top divided by delta V on the bottom. And if you look at this carefully, you'll see, anybody see an acceleration in there? Raise your hand if you can see. It's kind of a out of position acceleration. Sava, what do you see? No, V delta T, that's a distance. There is an acceleration, and that's the numerator there. There is an acceleration. Can you see it? It's not standing in its normal position. What's the definition of acceleration? Delta V over delta T. Do you see a delta V over delta T in there? Raise your hand. What do you see? Yeah, it's upside down. Good. Thank you. All right, so right in here, here's delta V down here, and here's delta T up here. So, okay, it's a flip-flop of the definition of acceleration. So we got an acceleration in here. Let's try to do a little bit of rearranging and stuff, and we'll find it. Okay, so I bring the V down here to the other side, and then I flip-flop everything, and I get delta V over delta T equals V squared over R. Go ahead and write that down. So we've cross-multiplied and rearranged things. And don't worry about doing the algebra for that. You can just write down this result down here. Now, this Excuse me. This right here is definition for acceleration. And so go ahead and write down A equals v squared over r. And that, my wonderful students, is the formula for centripetal acceleration. Right, so let's go to this next page. Because of proportional triangles, in other words, the speed triangle proportional to the position triangle, we have this formula for the acceleration. Now spell that carefully. Centripetal. Centripetal. Centri means center. Petal. We don't really have, I don't know of a word in English that's cognate with that Latin root, but it means toward. It's from the Latin word toward. Oh, you know what? Impetus. Impetus. That's giving something some towardness, I guess, in Latin. Anyway, centripetal force. There's another word that you sometimes can underestimate as a term, and that is centrifugal. And let me spell that. Go ahead and spell this one down. Centrifugal. Centrifugal. Now, centri means centri. That means about, the center, something about the center. And fug, there are English words cognate with that Latin root. Fug means to fly or to flee. Fugitive. Refugee. The Latin phrase tempus fugit, time flies. So centrifugal means something that flees the center. All right? So the word centripetal, you got it in your notes? Okay, you got it in your notes? Draw a line through it, cross it out, because we're never going to use it. This is, I saw somebody up in the front, you go, huh? Go on, Dr. B. Yeah, go ahead and cross that out of your notes. And don't ever use it. It's common to hear people say, oh yeah, man, the centrifugal forces. And in actuality, centrifugal forces, you can calculate those in special situations. For instance, if you have a centrifuge, which is one of the ways that they purify uranium. These guys over in Iran are trying to make centrifuges so they can get an atom bomb. But for us, centrifugal, no. We're going to be talking centripetal forces only, all right, toward the center. And centripetal acceleration. Here's the formula for centripetal force. And this is just F equals ma of using the centripetal acceleration. All right, it's just m times v squared over r. And you can write it this way, mv squared in the numerator and r in the denominator. And in both cases, you can see how the two parameters of the circular motion, the speed v and the radius of curvature r, are pretty important to this quantity. William DeClercq, you've got to go up to the physics department and get your ID card. I was up there yesterday afternoon, and you still had not nabbed it. You need it. Okay, now you're on the podcast now, so it's public that you. All right, so don't mess it up. Okay. Anyway, so centripetal force. If you have a lot of speed, that's in the numerator, and actually, it's the square of the speed. All right, so if you double the speed on your circle, that means the force and the acceleration that you need is 4 times as big. because you're squaring it. The radius is in the denominator, so if you have a big radius, that means a nice, slow, lazy turn. Big radius, slow turn, granny time, not too much acceleration, not too much force, because it's in the denominator. Right? So that's the way that this formula kind of varies. All right? And what we're going to do now, and for the next few minutes, is work on some examples of this. All right? So, and you'll have some homework this weekend, which I know has been burning you without homework for almost a straight week. But we're going to have some this weekend. I'll have it fixed up for you by lunchtime tomorrow, hopefully. And it'll be due next Tuesday. But let's get in a couple examples here. All right, you're driving in a circle in the Publix parking lot at 6 a.m., nobody else around. All right. And you're just trying to, calculate. Let's see if Dr. B's, on the up and up. So let's say that your circle is 80 feet. You're in the parking lot, so that's a pretty nice big circle. Okay, 80 feet. Now that's a radius of 40 feet, and in the metric system that'd be 12.2 meters, approximately. Okay, good. What's your name? You just got here late. So you're not one of my students? All right, good. I didn't recognize you, so. And you weren't exactly inconspicuous coming in through there. So, all right. All right, so there's your circle. So you're out in the Publix parking lot. Yeah, this is a realistic circle. You could do this. And go ahead and put a dot down here on. I got mine down the southeast quadrant of my circle. And I'm going clockwise. Here's my radius. And here's my velocity vector in red. And let's get that velocity and speed squared away. Let's say that you're on cruise control, 15 miles an hour. This is how you do uniform circular motion. It's got to be a circle, and it's got to be constant speed, so cruise control. By the way, I was watching the news this morning. They had this on ABC World News Tonight, or whatever it was. They had a blurb about a remote or a robot-driven car from Google, little teeny car, and they showed a guy that went blind driving around in this car, and it was actually the car that was driving, and he was taking a drive for the first time in many years. And so he would have computer control for the radius of turning and for the speed. All right, now let's say that your vehicle's mass is 1 metric ton, just so we have a nice round number. Okay? That Google car was probably smaller than that. Your vehicle's probably bigger than that. But this is, I'm sure there's cars that are 1,000 kilograms. No problem. So here's the specs. Speed 6.7 meters per second. Mass 1,000 kilograms. Radius of curvature in the Publix parking lot 12.2 meters. Okay, let's calculate this quotient here. Centripetal acceleration, v squared over r. And so we go 6.7 meters per second, quantity squared in the numerator. All right, so that's going to be 40 or, it's going to be a little bit less than 49, a little bit bigger than 36. And 12.2 meters for the radius in the denominator. All right, now do you have your calculator out? You better go grab it. And get your clicker out too, because as soon as we're done with this example, you're going to calculate one yourself, see how things go. Shy, I thought you were going to sit in the... Oh, okay. Okay, so 6.7 squared. Anybody got that? Who's got 6 point? What do you got in the black hair with specs? Yeah. 3.67? No, 6.7 squared. What do you got? Okay, 44.89. I like it. Here's your quotient. You're a couple steps ahead. Okay. Now I want to, and the reason I'm going step by step is, you know, a lot of people in here have had calculus, but a lot of people in here similarly are not so skilled in math. So I'm going to try to do it at a pace and without skipping steps that you can kind of keep up and ask questions. Now, here's my numerator, 44.89, and it's meters squared per second squared. Because if you square the 6.7, you also have to square the meters per second. All right, so this is what it looks like over here. Now, we haven't done anything with the denominator yet. But before we calculate that, I want to cancel out a factor of meters up here and one down here. So go ahead and cancel this whole unit of meters on the denominator and cancel out that squared up here. Now don't cancel out the meter because we're still going to have one factor of meters on top. And look at what we've got. Nothing happens to the per second squared, so that's good. And our leftovers in terms of units are meters per second squared. Good, that's an acceleration. That's what we want. So this is looking good. And now we go ahead and calculate to the nearest tenth, in this case 3.7. And the unit is meter per second squared. All right. So there's your centripetal acceleration. Questions before I proceed? Because you're going to need to do this in a few minutes using your eye clicker. Yes, Alexis. Yeah, because it's an acceleration. The question was, is the format always going to be meters per second squared? And the answer to that is yes, because we're trying to calculate a centripetal acceleration. Another question. Yes. Not yet. Not for the acceleration. But for the centripetal force, yep. So now we're up here with the centripetal force. Let's get this calculated. Because this one, yes, we do want to use the mass. Okay? And it's basically just F equals ma here. So it's 1,000 kilograms times 3.7 meters per second squared of acceleration. So we're good. And so that's 3,700. And notice that kilogram meters per second squared is the same as, and here it is down here. Okay, that's the same as a Newton. All right. And hey, you guys, sometimes it's nice to write an answer as a Newton, and sometimes it's handy to write the same answer in terms of kilogram meter per second squared. And why would that be? Well, sometimes if you're in the middle of a calculation, you might want to do some canceling. And so having a force as kilogram meter per second squared might be more conducive to canceling, stuff like that. So you'll have to keep your eye on that. All right, so let's go back to our notes here. The vehicle's mass 1 metric ton. Here's the centripetal acceleration, and here's the arrow for it. Actually, let me go back. Check out my arrow. I'm burning it in. Look at these flames. The flames of danger. Dun, 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 dun. All right, so there's centripetal acceleration. So draw in a centripetal acceleration vector toward the center with its tail at the location of your vehicle, which in my diagram is in the southeast quadrant, but you could have yours in any quadrant you want. And that is the centripetal acceleration. Now, the centripetal force is going to be pointing in the same place. So I'm going to draw in my centripetal force. Take a look at this. Here it is. There's my centripetal force vector in black. And I'm going to back it up, though. All right, so here we go. So now you can see both vectors. And sometimes you want to draw in the force vector. And sometimes you want to draw in the acceleration vector. They point from where the object is straight toward the center. All right, so you can see that from this diagram here. Okay. Now, on a test, like exam 2, coming up in a month or so, I might ask you, I might give you a set of 3 diagrams with vectors all over the place and labeled, and ask you to identify which one is the centripetal acceleration vector. And you would want to choose one of the vectors pointing from the location of the object toward the center. And not something that's tangent, not something that's pointing away from the center. That would be centrifugal. Right? I have to cross that out. And so it's that kind of visual discrimination, visual recognition skill is something I will probably test you on in some way, in homework and or in exams. Now let me pause for questions one more time. And how we doing? All right. Let's keep going. Let's try a calculation together on your iClicker. And it's a calculation. Let me get it started here. And it's very similar to the one that we just did together. But you're going to do it now. Let's see if you can do it without any coaching. Hold on a second. Let me try. I have to activate. Here we go. Okay, now you can try to calculate it and type, and I'll put the hammer down on the answer in just a minute. So go ahead and calculate. And remember, we're in lecture now, so kibitzing and conversing, talking with your neighbor is good. Mr. Perrone, are you here? P-E-R-R-O. Do you see my note in web courses? Yeah, you can take a look at it. I have your printout if you want it back now. Grab it after class. right? The nearest point, 0.01 of acceleration. Carl, you got it? Thirty seconds. Okay. 5, 4, 3, 2, 1, 0. Let me stop this question. See how you guys did. Whoa. I see some difficulties here. Hold on a second. Oh, no, we're doing good. We're doing 4.8. Whoa. Somebody had 3.788 times 10 to the 29. In other words, E29. I think that's a mistype. Anyway, the answer is, oh man, hold on. I was going to show you on the doc cam, but you guys know what you're doing. The answer is, bam, 7.35. And here, and if you missed it, here's all you got to do. Go ahead and write this down. 625 divided by 85. And that'll get you the right answer. Because 25 squared in the numerator is 625. And then the denominator is just 85. So numerically speaking, it's 625 divided by 85. Gives you an answer of 7.35. All right, now I may give you some more questions about this on the homework, and probably I'll give you some questions on universal gravitation, which is our next topic for today. So let's go ahead and start talking about universal gravitation. And this is a little bit more in detail than the e-text. So let's go ahead and start attacking this. Sir Isaac Newton figured out a lot of this stuff about centripetal accelerations. And it occurred to him that the centripetal acceleration for the circular path of the moon on its orbit around Earth might be related to the downward path or the downward acceleration of gravity for an apple that fell out of his apple tree, supposedly. So now here's what he was able to accomplish in his day. First of all, they had decent measurements of terrestrial acceleration. So they weren't in the metric system in those days, but it would have come in at 9.8 meters per second squared. So the legendary apple from the apple tree, using distances times measurements, he would have been able to get a good value for that. The other thing that they were able to do was estimate the moon's centripetal acceleration. And the reason that they could do that is because they knew the distance to the moon from Earth, center to center, as a multiple of Earth's diameter. And Earth's diameter was known in his day. Now, they would have measured it probably in miles, actually, they might have measured it in leagues, like 20,000 leagues under the sea, 20 league boots. Yeah, back in his day, they might have used leagues. Anyways, they had a fairly good handle on Earth's diameter. And of course, they knew the orbital time to the nearest second, about 27.3 days for one lap of the moon around the Earth. All right, so we know the diameter of the circle. We know it's r. We know the amount of time it takes. So we know the r, we can figure out the circumference. And so that's how many miles, kilometers, or leagues that you go every 27.3 days. So then convert 27.3 days to seconds. It's a big number. And then do your quotient. And here's what he was able to estimate. That the centripetal acceleration under the measurement that he was able to do in our current metric system was about 0.027 meters per second per second. All right? And that is roughly 1/3600 of the surface acceleration in his apple orchard out in the backyard. So he's up there, and like any egghead, he's daydreaming about this and that, or probably thinking about some chicks or something, or maybe pizza, or whatever he was thinking about. And he observed an apple falling, so they say, and he was able to put these two things together. The other kind of interesting thing is that the radius of Earth is about 1/60th of the distance to the moon. So, so here's the two things you've got. You've got distance, the ratio is 1:60. Acceleration, the ratio is 3,600 to 1. Now, 3,600 to 1, that's 60 squared, 3,600. And the question is, was that a coincidence? Which it could have been, but Isaac Newton said, nope, I have an idea that that is not a coincidence. Here's another look at it. If you actually calculate the numbers, this is the proportions. So if the acceleration is measured as 1g, then the acceleration of the moon on its circular orbit, its almost perfectly circular orbit, is 1/3599.6. That's pretty darn close to 1/3600. All right. The distance in terms of Earth radii is 60.3 to 1 Earth radii. So the distance of the moon center to center is about 60.3 Earth radii. All right? And as I mentioned before, that this acceleration down here is approximately 1/60 squared. So this is like, this acceleration is measured in G's. It's here on the surface of the Earth. the apple from the apple tree that conks you on the coconut is accelerating with 1 g of acceleration. That's a g. The moon, way smaller than a g of acceleration. Now this diagram down here, here's Earth down in the lower left, and here's the moon, this little teeny circle. And that, my wonderful students, is the true proportion of the geometric relationship of Earth and moon. So in other words, if the Earth were this size, then the moon would be this size up here and that far away. If you've ever seen here, and so here's another note. So try to make a sketch of that as well as you can. And then here's a side note. If you take a globe of the Earth, you know, like from 6th grade, you know, on your teacher's desk, you know, or you may have one at home, a regular globe of the Earth from a classroom, then the moon would be the size of a tennis ball. And it would be about 27, 28 feet away. All right, so that's from Sava. Can you stand up? Okay. So Sava, can you move up a little that way? All right, that's maybe 20-something feet. So if the globe of the classroom globe of the Earth were here, and if Sava was holding a tennis ball, that would be about the right proportions on that scale. On this scale, to fit on, thanks Sava, to fit on this slide, you know, I measured this out really carefully. It's very difficult to do because most textbooks, they draw the Earth like this, and then they put the moon the right size, but like 2 inches away, and it looks like they're at the same orbit as the space shuttle or something like that. But the moon is way out there. Way the heck out there. 250,000 miles. So here's the conjecture. Gravitational force, gravitational acceleration, is it dependent on the inverse square of the distance, 1 over distance squared? Because that's what this table kind of tells you. Here's your distance ratio, 60:1. And here's your acceleration ratio, 1 to 3,600. That's 60 squared, pretty close. All right, so does that mean that the gravitational force depends on the inverse square of the distance? And Sir Isaac Newton says yes. He said that in universal gravitation, in other words, terrestrial and celestial, the apple falling out of the apple tree, terrestrial, and the moon circling around the Earth, celestial, that same force affects both of them. So it's universal, everything in the universe. And it depends on only 2 physical factors. First of all, the mass. It depends on the mass of the object, each object, and their distance apart, and that's it. And Sir Isaac Newton said, it's not just the distance, it's the square of the distance, and the square of the distance is in the denominator. So let's try to put it all together. First of all, the more mass, the more force. So if you do have a quotient, the mass is going to be in the numerator. If you have more distance, you have a weaker force. And you can see that by the accelerations. The acceleration of the apple, 9.8, 1 g. The acceleration of the moon, 1/3600th of that, approximately, on its centripetal, or for its centripetal acceleration. Now, here's the formula that Sir Isaac came up with. Okay, the force of universal gravitation. So this is a little subscript g here. And here's your numerator, a big constant called Newton's constant, or the gravitational constant, capital G, times the mass of one object, m1, times the mass of the second object, m2, and then divided by the square of the distance between them. All right? And this particular law has been extremely well verified. Newton developed a lot of concepts using calculus. NASA uses this all the time. If you want to park something at a certain location on Mars, you know, you want to land it there within a few meters, within a few hundred meters, you better know this, among other things. Question. The big G is called Newton's constant, or the gravitational constant, and it is a constant of proportionality, okay? Or you could call it a conversion factor. All right, now here's how you can think about that. This side over here is a force. So a force has to be kilogram meter per second squared. But we don't have any seconds over here at all. All right? We have some distance, but it's distance squared. And we have mass, we have some kilograms, but it's kilograms squared. Okay, so this constant here, capital G, converts all that into newtons. Kilogram meter per second squared. Here's a way to think about a conversion factor. You know, when you're converting from Fahrenheit to Celsius temperature, you have to use a factor of 9/5 or 5/9. You know, then you got to subtract or add 32, and you know it's kind of a pain in the neck. But 5/9 does for Celsius to Fahrenheit something like what capital G does here for gravitational force from these two different kinds of measurements. So normally a force, you would have to know the mass of the object, its acceleration, meters per second squared. But what Newton was saying is that there's a natural force that only depends on the mass and the distance squared. Okay? And so if you know these factors and you know G, you can figure out how many newtons you got. And that was his genius. Let's keep going. Would you guys like to dismiss early today? What do you think? Maybe? Okay. All right, let's take a look at an example. Let's take a look at a gravitational system of Earth, capital M, and a satellite, little m subscript s. And let's say that, you know, NASA wants to put it at a certain distance above the Earth on its orbit. And NASA's going to put it up there with rockets, the way NASA does. And if it's a circular orbit, we can kind of hack it pretty easily. All right, so let's say that we're putting a spacecraft up there on a circular orbit. Now, the force that keeps it on circular orbit is gravitational, according to Sir Isaac Newton, and we've verified it many times. For that reason, this equation this is what F equals ma turns into. All right, Newton's second law. Here's my force, gravitational. Depends on the mass of the Earth, capital M, the mass of the spacecraft, m subscript s, and the distance that NASA wants to park it. You know, and that's a distance from the center of the Earth. And then on the right side, if it's on a circular orbit, automatically you've got centripetal force. So it's the mass of the spacecraft times v squared over r. All right? Now what that means is that, and here's the gravitational part, and whoa, let me go back to that. Okay, there's the gravitational part, and over here is the centripetal part. All right. And if you look at that carefully, you can simplify that fairly nicely. So let's take a look at that, see if we can simplify anything. Anybody notice something to simplify? What do you notice?
Actually, I was going to say something else.
Say something else then.
We just, LIGO has just detected gravitational waves, confirming a theory that Albert Einstein had in 1960. They adjusted that.
You mean that was just, they just blasted that out on the news? Nice. LIGO. What is your name again? Megan. Megan just said that the LIGO observatory just detected gravitational waves for the first time. LIGO, Laser Interferometer Gravitational Observatory. It's basically a set of big tunnels down which they shine really precise laser beams, and then they look for oscillations in the, and they beam a laser beam reflected off a mirror, and then they look for oscillations in the mirror. And I believe they've got locations in Washington State and Louisiana. And I think maybe they've got one over in Germany somewhere as well. The Laser Interferometric Gravitational Observatory. So detecting gravitational waves is much more difficult than electromagnetic waves because gravity is really weak. And the reason gravity is weak, Megan, is because this constant here is pretty small. The electromagnetic interaction, as we'll see in a couple weeks, looks almost the same, except it has a different constant, and it doesn't depend on the mass, it depends on the electric charge. You know, how many electrons or how many protons. And so LIGO, very good. Thank you for letting me know that. Now, back to from the news update. Back to our task at hand. Do you see anything in there that can simplify? What do you see?
Well, I see a v squared over r.
No. I mean, it's good. I mean, v squared over r is in there, yeah. Yeah, so that's your acceleration. But is there any simplification you can do for this big old monstrous equation? Don't go like this. You're faking me out. I think you're do you have the what? The satellite? What about it? The satellite on I don't see a satellite on both sides. What do you see on both sides? The mass of the satellite. Okay, so yes. That's what you meant, right? Okay, so go ahead and burn those babies. All right, and here's your leftovers. G times capital M, the mass of Earth, divided by the square of your orbital circle. All right, and then we got an R over here. So this is looking a little dicey here. Let's clean it up a little bit more. We can cancel one of the R's. And we still have one over here on the left, though, so we can't get rid of that one. But we can get rid of this one over here. And so now we have v squared on the right, r on the left in the denominator, and the numerator is capital G times capital M. Now, those are two constants. So make a note, capital G is a constant, the mass of the Earth is a constant. Pretty much. And so when a spaceship blasts off into space, it's no longer part of the mass of the Earth, but it's a pretty small fraction that you're losing. So we'll just call that a constant. All right, so Gm over r equals v squared. Now, let's think about what that means. If you know the radius r for the orbit, you can then figure out the required speed, v, and design your rockets appropriately in order to achieve that. And what kind of an application would that be where you want to put a satellite up at a very particular level? Well, one example of that is if you want the satellite to be in low enough orbit that its cameras can keep an eye on the Russians. And the Hubble Space Telescope is up there looking out at the universe, and I guarantee you, I almost use a cuss word, I guarantee you that the CIA and the Department of Defense have about 75 zillion Hubble Space, well, maybe not that many, but they have a bunch of Hubble Space Telescopes, or the equivalent thereof, looking down at Earth. And as good as the Hubble Space Telescope is, think about reading some Russian's driver's license, because that's what you can do with that thing. And that's why they got those up in space. You're reading his mail. Now, if you need a certain orbital speed, all right, then this tells you, all right, where do you park it? You know, and you might think to yourself, all right, why do I want to have a satellite at a certain elevation, a certain radius? Well, you might want to have one that is fast enough to orbit once per day. You know, so in other words, you got some satellite up there, and it's basically, the Earth spins once per day. Once every 24 hours, and that thing's circling the Earth once every. So basically, the Earth is spinning at the same rate that the satellite is going around, and as a result, it never seems to move. You look at it here from Orlando, and it seems to be stationary. And that is called a geosynchronous satellite. And we use those for communication. If you've ever seen, or if you at your apartment have a direct TV antenna, or dish network, or something like that, or if you've ever seen, like the TV trucks, they have a big antenna on top that they aim in a very particular location to beam stuff back, to national headquarters in New York or wherever they're beaming it. That is, they're locating and transmitting to a geosynchronous satellite. And your dish network, your direct TV antenna is listening to the emissions from a satellite up there. They're beaming ESPN and everything else from that satellite up in space with just enough power to get to your house with a little bit of power to spare, unless it's really raining. And then the rain attenuates the strength. And does anybody ever notice that in DirecTV, if it's really raining hard? Raise your hand if you've ever noticed that. Yeah, if it rains hard, you sometimes lose a signal, even if you're not on satellite TV. Okay, so those are two examples of how centripetal acceleration concepts and universal gravitation concepts can help you manage your space program. Whether you're trying to keep an eye on the Russians or you're trying to talk to somebody on the ground. Hey, raise your hand if you've ever used a satellite telephone. Anybody in here ever done that? I've heard of them, but I've never actually seen one, and I've never spoken one. Anyways, satellite telephone, same thing. You're talking to a geosynchronous satellite, and then it's beaming the conversation back to the ground somewhere, and you're having your conversation. All right. Homework for the weekend, I'll have it ready for you by lunchtime or so tomorrow. It'll be due Tuesday. You are dismissed. See you next week. And Caroline has your exam printouts. If you didn't get them yesterday, come get them up front.